Okay, this video is all about protein hydrolysis. Protein hydrolysis is all about breaking peptide bonds. We're going to break peptide bonds to form amino acids. We're going to break up these di and tri and polypeptides into their individual component amino acids. So, this is like taking amino acid 1 that's bonded to amino acid 2 in a dipeptide. We would add water. To that, we would need an enzyme. And then we would form individual amino acids. Amino acid 1 separate from amino acid 2. So we're really breaking apart the amino acids. So a couple of things. How do we do this? Well, it's pretty simple. Step 1, just find your NCC. Find NCC, that amino acid backbone. I'm just going to write AA backbone, right? Find your individual amino acids. And then, really find and break that peptide bond. Find and break your peptide bonds. Okay. So let's first look at this tripeptide. We have NH3 plus bonded to CH, and that CH has a nonpolar side chain, so an alkyl side chain. It's actually CH with a CH3 and a CH2 and a CH3. And then it's bonded to C double bond O. So that makes up our NCC backbone. Our first nitrogen, then our central carbon, then our C of our C double bond O. That's our NCC backbone. That C double bond O is bonded to an NH. There's our new, our next amino acid. That NH is bonded to a C that has 2 hydrogens on it. And then it's bonded to another C. So there's our next NCC. C double bonded to O. It's bonded to a nitrogen. So there's our new nitrogen. Bonded to an NH. That NH is bonded to a CH. That is also bonded to a CH2 that has a benzene ring on it. So this phenyl group, that's why it's phenylalanine. And then it's C, double bonded to O, and then bonded to an O minus. So we've really found NCC, NCC, NCC. That's our job here. Now, where the C of one amino acid is bonded to the N of the next, that is your peptide bond that we want to break. So we are going to need to add a water across each of those peptide bonds. So we need to add a water across the first peptide bond, this one that we're trying to break. We're going to need to add a water across the second peptide bond. This shows a third water molecule, but we would not use, we just need 3. We don't need 3 water molecules. We just need 2 water molecules to break our 2 peptide bonds here. If we have a tripeptide, there's only 2 peptide bonds holding the 3 amino acids together. We only need 2 waters to break that apart. And so what do we end up with? We end up with our 3 separate amino acids, isoleucine, glycine, and phenylalanine. And let's see. Sorry about that. So each of these are shown actually in their zwitterion form when the tripeptide has broken apart. So that is great because that's how they're naturally going to be, and they're shown as, separate amino acids now because they have been separated by the hydrolysis. The idea is this, like if I'm looking at, say, isoleucine, say the first amino acid in the peptide, if I'm still looking at the tripeptide, the carbonyl carbon, the C double bond O, that one needs to gain an OH. And then my nitrogen of the next amino acid, that needs to gain an H. So, that's where the H and the OH of the water need to go when this dipeptide bond, or when this peptide bond is broken. Okay, so let's look at just one more example. So in this, we've got a polypeptide. Really, we're starting to look at polypeptide, where we have more than just 3 amino acids. This one actually, let's count up the amino acids together. So we've got NH3+, so that's our first N, bonded to CH, bonded to C double bond O. Now that central C had a side chain, CH2 and a benzene ring and an OH. Okay, but that's our first NCC. Then we see NH, bonded to an NH, bonded to a C with an H up and an H down, bonded to a C double bond O. Then that's bonded to, so let's just take a step back. Our first NCC was bonded to a second NCC backbone. So there's our first peptide bond. Now our second NCC is going to be bonded by a second peptide bond to NH, bonded to CH2. So we've got NC, and our last C is double bonded to an oxygen. So that's our third NCC. Now there's a peptide bond, and that peptide bond is, of course, to NH, bonded to a CH, which has CH2 and a benzene ring on it for a side chain. And then it's bonded to a C, double bonded to an O. So that is our 1, 2, 3, 4th NCC. There is one more peptide bond, it looks like here, bonded to an N, H, bonded to a CH. That CH has an R group of CH2, CH, and then with CH3 too, so 2 CH3s on it. And then that central carbon is bonded to a carbon, C double bond O, bonded to an O minus. So that's our carboxylate group off on the end. So what do we have going on here? Well, we had, let's see if I can get my pen. We had NCC, peptide bond, NCC, peptide bond, NCC, peptide bond, NCC, peptide bond. So we had 1, 2, 3, 4 peptide bonds. For those 4 peptide bonds, we are going to need 4 water molecules to break those 4 peptide bonds. So we go 1, 2, 3. Just trying to show kind of in between 3. And then we'll need a 4th water molecule here. So I'm kind of showing that the 4 waters should basically go in between the amino acids. That's how I like to think of it, is that these waters, kind of have to go in between these amino acids, breaking these peptide bonds. Okay, so we end up with our separate amino acids, 1, 2, 3, 4, 5 separate amino acids. We needed 4 water molecules. Why? Because we had 4 peptide bonds to break. So I'm just going to write down 4 peptide bonds were broken. Woohoo! Now here we're showing each of the amino acids as Zwitter ions, which, let's do shown as Zwitter ions. Now, whether or not each group's going to be charged will depend on the pH of their environment, but in general, it's more natural and common for them to be in their Zwitter ion form. Hydrolysis like this of our peptides and of our polypeptides does require a catalyst. So let's add that. Hydrolysis, and these are enzyme catalysts in the body. Hydrolysis requires catalyst. And okay, I forgot a Y, an L there, catalyst before I seem to be forgetting letters randomly as I notice here. Hydrolysis requires a catalyst. And so in the body, you know, that's going to be an enzyme catalyst. So again, we are taking our amino acids and we are breaking the peptide bonds that hold them together. There's always one fewer peptide bond and one fewer water molecule needed than we have total numbers of amino acids. It's more natural to show them in their zwitterion form, but their actual charges are going to be pH dependent. You know, if you put it in an acidic or a basic environment, that could change that. And hydrolysis is going to require a catalyst like an enzyme.